All right. Good morning. Welcome. We will continue to introduce hashing in chapter 27. Now, from the lecture in the preceding class, you have the idea. What is hashing? Hashing is essentially, it's a hash table. And hash table is implemented in an array-like data structure. So it's array or using array list. To access the elements in the hash table, we use the index. So given index, we can access the element, insert the element, and remove the element all in all of one time. So this is a constant time. It doesn't matter how big is hash table. So this is the hash table is depending on the data. So if you have large amount of data, your hash table is always larger than your data size. When you store the data into the hash table, and data is mapped into the key through the hashing. So there's a hashing function to do this mapping. So this is a real simple diagram. You can see it. It is this here, the diagram. And this is the diagram right here. This is the one here. It's in this figure 27.1. So it is the key right here. And here it's a data. So the data itself or part of data is the key. So that's used. And for this hashing function, you get this index. And this is where data is. All right. Now, you may have two elements, different elements that mapped into same location. So that's called a collision. And how we deal with collision, and we talked about this last time, it's to use the linear probing, quadratic probing, or double hashing. So this is what, and we looked at the last time. And so let's look at this. All right, how you handle collisions and using this linear probing, quadratic probing, and double hashing. Now this three techniques, it's in the category of open addressing. So this is the open addressing. This is all they do is to find an open location in the hash table. If you want to insert a new element, so you use the hash function and to locate the location and the index. So if there's element already in that spot, so what you're going to do, use linear probing, quadratic probing, or double hashing to find an available open spot. All right, so this is all open addressing. We talked about this last time, and open addressing, and here. All right, so there's actually a better way to do it. It is it's commonly now used in all the implementation, the system API implementation. It is the using separate chaining. So let's now look at the separate chaining. Separate chaining is this. You have this hash table, but each entry in the hash table is a pointer to a bucket. All the elements mapped to the same location are put into the same bucket. All right, so now let's look at this example here. We have this is the table size is 11. And this is the key is 44. So 44 using this mapping, it's 44 remainder 11, it's 0. So now it is this, the bucket has 44 here. All right, so here, this is a 4. It's in the bucket now, and location is index 4. And now comes 26, and 26 is also here. Now, using separate chaining, we just put 26 in the same bucket with 4. So now we're not looking for open spot like the open addressing approach. This is using separate chaining. So separate chaining is for the elements mapped to the same location, they're put into the same bucket. All right, so here's animation. So let's use this animation, and we're gonna see here, if I have, this is the one here. So let's use 12. So where 12 goes, 12 is going to be mapped to the location at the index 1. So we're going to insert it now. It is this. Here's 12. Okay. All right. If you look at the usage for this animation, you're going to see this. We have this is the current table size. So current table size 11, you can change it manually here. This is the size 11 right now. And this is the number of keys is 4. All right, so if you remove 12, see what happens. Remove 12 and the number of keys is now reduced by 1. So it's becoming 3. So if you insert it back, it's becoming 4. So, all right. Now you also see here, there is another parameter. It is current load. So what is the current load? It's actually its load factor. There's a load factor. Load factor is this. It's a measure. It's measurement and to measure how full the hash table is. So how full it is. So this is 36% full. So you have 4 out of 11. That's 36%. If you reduce this, remove 12. Let's remove 12. It becomes 27%. All right, so that is the load factor, the current load factor. So there is another thing is here, it's a threshold. Load factor threshold, it's 50%. So what does this mean? Means here it's 50% is always, you have to be, cannot exceed 50%. The load factor, the current load factor cannot exceed 50%. So this is just a threshold, and why we need the threshold? It is this: if your table is very, very full, and the chance of collision is high. So, like here, you have this is separate chaining. So you have this is 12 inserted, and you may have inserted another one. So your bucket size will be very large. And then the time for search, insertion, and deletion, and will cost more. So if your table is very sparse, and the chance of collision is less, and the operations for search, insertion, and deletion will be more efficient. So that is the consideration for this threshold. 50%, you can increase it or reduce it. You can set this threshold. So setting this threshold here, you can set it. It is just a matter of your decision, and you how you're going to manage your data structure, and you if you want it to be really efficient, fast, and you're going to sacrifice on space. So if you have a constraint on space, you're going to sacrifice time and to use more space, to use less space. So that is the just some decision you have to make. In general, and I think it's in the system by default, it is set as 75%. It's set as 75% in the system. But now, see here, if you reset it, so this is the 75%, so 75%. But I'm going to set it back to this 50%, still 50%. All right. All right, I'm going to show you here is, let's add more things here. I'm going to add, say this is 12. All right, I'm going to add 23. So where 23 goes? 23 is going to be right here at index 1. So I'm going to insert it. So you see 23 is going to be here. All right, so this load factor is 45%. That is still fine. Under 50% of the threshold. Let's continue. Let's have another one here. It's this. I'm going to have 34. All right. If you go with 34, so you're going to see this is the total. It's going to be 6 out of 11. It's going to be exceed 50%. So now what happens? Okay. It's going to, you have to maintain this. It's the load factor is on the threshold. So we need to increase the size. So it's the size is going to be automatically increased and more than doubled. Just see what happens. It's 11. So we're going to see the next. We're going to insert it, and then you're going to see the size is doubled, and the table size is doubled. And all the elements are going to be rehashed and reinserted into the data structure. So let's do insert now. All right, as you see here, this is the new size. So it's 11. So now its size is 22. And this is all rehashed. So this, it's all rehashed. Now you see, this is the 12 is here, okay? And 34 is here, and this is now the new internal storage, okay? And the current load factor is this 27%. All right. If you look at the previous section, so if you look at the previous section, when we introduce open addressing, and we have the same parameter here. So here, this is the animation. And you see we have the current table size, 11, number of keys, and see this is right now is 5, yes. and the current load factor, this is 45%, and this is the threshold is set as 75%. Okay. So if you add more, right? So you can add, let's add 34. Okay. So the threshold now it's still 75. This is under 75. The current load factor is 55%. And so let's add more, 24. All right, so now I think you go the next one, 7 and 75%. Maybe you can see this is 34. Let's do it 36. All right, so it's right now it's 73%. Okay, and if you add one more, okay, add one more, it's 43. All right, see what happens. We have to do rehash. It's increase the table size and now do rehash. Okay. And here is using linear probing. All right, so all of this is discussed actually in this chapter here, section here on the load factor and rehashing. So this is the section we just covered, and using the animation and look at the parameters in the animation. So what is the load factor? What is the threshold? And so the current size and the table size. Okay. All right. So with all this, now we're going to implement our own hashing. All right, so we're going to do this. Implement a map using hashing. So we're going to have a hash map. So here in the Java API, we have map. So I'm going to call this as my map, just to make it different from the Java API. So this is called my map, but all these methods are the same. Clear. Remove all entries from this map. Contains key, returns true if this map contains an entry for the specified key. Okay, so here's contains value, returns true if this map maps one or more keys to the specified value. Specified value is in the map, so this is the return true. Entry set, so we get all this entries in the map and return it as a set of entries. So get, you get the value using the key, is empty, so returns true if the map contains no entries. And the key set, get all the keys and put it in a set of the keys. So put, that's the one you're going to insert and this entry into the map, the key and value. So this is remove. Remove an entry using the key. Size returns the number of mappings in this map. Values, so you collect all the values and return it as a set of values. All right, so here we're going to have this entry set. This is the entry. How do you define the entry? Entry is here. So here is, this is the entry here. This is the entry here, is a key and value. Simply just key and value, and this is forming an entry, and get key and get value. So this is the entry here. All right, so now this is the a concrete my hash map. So my hash map It's everything is here. It's already defined in my map, and we just inherit it. And so this is all the constructors here, 3 different constructors. So now you can see this is no R constructor, and this is the constructor with specified capacity. Capacity is the table size. And there is another constructor. We now specify the load factor threshold. So if you and go back to the chapter on sets and maps. So let's go to that chapter now. So I'm going to go to that chapter, and you can see this. So we mentioned this when we look into this in the Java API and the hash set and hash map. So look at this set right here, and you can see this is the UML diagram, and you see this is the constructor here. There's a load factor here. So now you understand what is load factor. This should be this threshold. This is when you create a hash set, you can specify the load factor threshold. This is essentially, this should be the threshold. So we're gonna go back here now and see this one right here. All right. By default, we can specify a threshold. What is the threshold? Threshold is 75% for load factor. Okay. And by default, the capacity is 4, so really small here. And this one here, you specify capacity, but you did not specify the load factor threshold. That's 75%. So here you specify both capacity and load factor threshold. All right, so now we can write the code. This is design. Just it's easy because we just copy it from the Java API. Okay, and so now we're going to implement it. And implement, easy for my map is just simply you just write everything here. Just write the code from the UML diagram. So we write the code. So here's a public interface. It's my map and key and value. And here, and so you have this is return true if the specified key is in the map. So what is this? It's public boolean. And so that's the one here. It is this contains key. So here is contains key, and here is the key. Okay. All right, so you can write all this. And so what is this? Here in this interface, and we define this static class. So you can put a static class here. And so this one is entry. So here's a key value. So here is this is key and value. So you form an entry and using this key and value. So here's get key, and that is simply return, and this dot key. So this is get value. So here is the toString. So you get this toString is this. ToString is this. Okay. This key and value separate by comma and space, and then in this square brackets. So here's my hash map. My hash map implements implements my map with key image. All right, so here we have this default initial capacity is 4. Okay, so there's one thing here is this is the maximum capacity. Maximum capacity, we make this is the 2's power raised to 30. So using this operator, this is the bit 1, you're going to do a right shift 30 times. You shift 1 time is multiplied by 2, another time multiplies by another 2, so that's here, you multiply 2 30 times, so that's what you get. It's 230. This is the maximum capacity. Suppose this is the you have some limitation on your memory, so you have to set the maximum capacity. All right, so this is the current capacity in this my hash map, and here's the default max load factor. This is the threshold. It's 75% of the threshold. All right, it's maximum. This is default max. Okay. Okay. And this is the here's number of entries in the map. So what is this number of entries in the map? So here's the size. Okay. Well, this initially is 0. So that's here by default it's 0. All right. So now we need to look at this table. So we're going to implement this using separate chaining. All right, here's a table. So what is the data type for this table? Think about it. What is going to be the data type for this table? So we can use using we can use array or using array list, but I think what I'm going to do is let's try this is using an array. So, and then we can manage ourselves when its size changes, we're going to double it, so we can manage that. So what we do here is this is the data type. So what is the data type? It has to be the so when you write array, you write something like this, brackets, right? So what is the type, data type for this? It's
integer.
It's not an integer. It's going to be entry. It's entry. So
oh, you mean for the element of the
yeah.
hash
So for
map?
this,
okay, never.
Yeah, for this, so if you look at this here is the hashing here. So we're going to go this. Okay. All right. So if you look at this, you can say this is, you can, what each element, the data type for each element here, it's a bucket, right? So what is the data type for bucket?
Would it be correct to call it a key value pair?
The bucket is not the bucket itself. It's a list. We can use array list. So this is something when you write, you're going to write something here is right here. It's the data type. It's array list, and each of this is an entry. So the entry is defined right here. Entry is here. Entry. So entry is defined here. Entry here. It's right here. Entry. Okay. It's in my map. So you're going to write it as my map dot entry key and value.
I have a question.
Yeah.
So why is it that we don't just use the interface map.entry? Like I guess since we can't instantiate it since it's an interface, is there any like default implementation that Java has, or do we have to implement it ourselves?
Yes, you can use the one from Java. Yes, that's fine. Another thing, I just let you know that I think what I'm trying to do is a linked list, but you can actually use either linked list or the array list. So here, I just look at the import. It's imported to linked list. So either way is going to be the same effect. So I'm going to change this to linked list. So look, what you're saying is that you can just use the one from java.util.map. Yes, this will be fine too. Okay.
Okay.
So, but the ones I'm using, I already used everything from scratch from myself and implemented.
Right. So if you did have like the actual objects being implemented in your custom type, I mean, assuming you don't inherit any of the behavior from Java's map or entry interface, you have to use that one, your custom.
Yeah. So, but
Okay.
if you use map, look, if you want to use map.entry, okay, then you have to change also here. You don't use this anymore. Here, look here, entry here, you have this entry right here. You have to use this here. You have to delete this part. Delete this. Okay, and then you have to say this one here and just to import it, or specifically you can just put it, and you have to be using the same thing here, java.ut.entry here. Yes,
okay, I appreciate
that
it.
will work. Yeah, so that's really good. And we have the source code and here, and you can test all this and make modifications and see how it works. Yes, good. Okay, very good. Yes. All right. So I'm using just stick with the one I have. It's in the using my map here. All right. So this is really the key here. You need to understand here the table is this. Okay. So look at this now. This diagram. This is the just simple diagram, and we have this is the an element. But now our element is this. It's an entry, key and value. So you have key and value. So this is an entry. So here, this is an entry. So this is entry. So look at the whole thing. It's a list. So you can use either array list or linked list here. And this is the element. So the table, each element in this table is a list of entries. So that's why we have list of entries for the table. All right, so this constructors, my map. So now we're going to just use this using default initial capacity and default max load factor. And here, my hash map, another constructor. So we use this initial capacity. Here is the initial capacity right here. And this is the default max load factor. And this one here, that's the one. So all this using this, and this comes to, well, comes to this one. Here is initial capacity and load factor threshold. So now we can look at this. If your initial capacity is greater than the max capacity, so then this cannot be allowed. So I'm going to just use the max capacity, okay, to replace that. All right, so this here is else. How do you get this capacity now else? So this, if the size is within the range. So we do this is you're going to trim to power of 2. So if this one here, let's say is so you're going to initial capacity, you have 20. Let's say you use 20. Use this, you pass a value of 20 here. Pass a value of 20 here. All right. So you're going to pass a value like 20 here. You pass this value of 20 here. Okay. So it's 20 here. All right. I'm going to do the trim to power of 2. It's going to be trimmed to down to the nearest. It's going to be 16. So I want to be the power of 2. The reason is some for internal purpose for efficiency. So we know it already. If the size is the power of 2, when you can use bit operation to map it to the index. Instead of using remainder, we're going to use this the bit operation. Use the bitwise AND. So you're going to see this in the implementation now. So the capacity. All right, I'm just going to remind you one. Let's go back to the one why we're doing this. So we do the trim to the power of 2. So let's go down to this here and just look at this hash code. Okay. Compressing hash code. So please read this part. Why we're doing this. It's remainder and it's the same as bitwise and n minus 1 for this n to be the power of 2. N is an integer power of 2. Okay. All right. So that's the reason we're going back here. Trim to power 2. You're going to look at how this trim of power 2, how we do it. So if this initial capacity is 20, it's going to be trimmed to 16. If this is like if it's 33, it's going to trim to 32. So this is okay. All right. So here's load factor threshold is the one here. We have this load factor threshold, and right here the table. So the table we did not create it right here. We did not create any table here. So we need to create the table here using this size. Now we have this. This is the capacity here. So here is new. So we're using linked list. Okay. And this one here is my map dot entry. Okay. I'm going to show you here. There's something here. Is you normally you're going to use can be here, but you should not just use this. Yeah, should not use this. Here, use this is the brackets is this dot capacity. Okay. All right. So how you're going to implement this contains key. Think about it. How are we going to implement this contains key? Is you're going to return true if the specified key is in the map. Okay. So if the specified key is in the map, so how do you know if this is in the map? All right. Okay. I want you to go back to read this after this class so you can read it. So how do we do a clear? So clear, you can remove everything, right? You set size to 0, but you have to remove all the entries. So you have all this entries are removed. So this has to be done. And for this, so what we do contains key is there's a method we're going to implement the letter. It's a get key. So there's a get key. So if you use this get key, what you're going to have is this is get key. So this get key, if it is not null, so that you're going to return true. So here, look at this get key is right here. So it's return the value that matches the specified key. So returns this. But if it doesn't match anything, so you're going to return the null. So this is return null. So that's why we're going to use this get key. So this is here. All right. Just things. This can be simplified with just one line. So we're writing this 4 lines here. So you can just simply say, I'm going to return this right here is not null. If this is true, it's going to return true. If this is false, return false. So like this. All right. I'm going to get this more on this. I'm going to talk about more. There's a lot of details. So please read it, and I'm going to give you some discussions in the next class.
I have a question.
Yes.
So that method where we do contains key,
Yeah.
I know it uses the get function, which basically
Yes.
it looks like it calls the hash function inside to obtain the value. Is there a way you can check if the key is present? Like if there is a key matching that without having to do the whole hashing function?
You have to do. This is the data structure here. Your entries are stored in the buckets. So you first need to locate the bucket, and then you get into the bucket to do a search, linear search.
Okay.
Yeah.
All right.
Okay. So here's the idea is that the bucket size is going to be very small. So if the bucket size on average is going to be very large and your data structure is not efficient, your bucket size is very, very small. So that's the assumption. It's actually, it's in practice, that's the case. That's why it's so efficient, because the way you get the bucket index, it's constant time. And then you get into the bucket to find it, it's constant time. Okay, very good. So please, this is something I want you to really get to this. It's a very elegant way to implement this data structure. It has a lot of interesting details, so it's very, very good data structure, and you're going to appreciate it more when you get into everything. All right, any other questions? Okay. All right, we're going to meet again this Friday, and now I have an announcement. After this chapter, we're going to have exam chapters from 22nd, chapter 22nd, and to chapter 27th. chapter 22 to chapter 27. And the exam is going to be on Monday, October 30th. Okay. All right. So please and put it down on your calendar. And the format of the exam, it's the same as the previous one. So I think this time you're going to just write one program and do 20 multiple choice questions. So this one program will be part of a very large program. So I have a large program, but you're going to only write a small part of it.
Are we going to try using that platform again, or we just...
No, you just submit it and to Folio. Yeah.
Okay. And it's week after next, right? October 30th?
Yes.
Okay.
Yeah. Yeah. Mhm. Okay. So you have some time and to prepare for this. Yeah. Mhm. All right. So this will be our exam 2, and then we will have the final exam. So in sometime in December, the early December. Yeah. All right. Any questions? Okay. If you have questions, then please stay. Goodbye.
Have a good one.
You too. Bye. Thanks. Any questions? Cole? Salam, any questions? All right, I'm going to stop recording.